Sorry for the delay in this recitation. Okay, so the agenda for this recitation is basically talk a little bit about KKT conditions, a little bit more. Then jump to penalty methods. Finally, the interior point methods. Right, so this is like roughly what I'm going to be talking about for this recitation. So for first KKT conditions, I'll just give you a example which Ryan mentioned in the class, like we're covering the water filling. So this is like a very cool example for like understanding the advantage or benefit you get while using the dual rather than just the primal. So imagine you have like some 10 channels of communication, so like 10 or 100, so n channels, 1, 2. You have n channels of communication, so you want to send some bits through each of these channels, right? So you want to send, for example, just say 1 bit, okay, one fraction of the bit, right? So now you want to send bits along each of these channels, so you send alpha 1, alpha 2, sorry, channels. So you want equal one, you want, so you are sending this many fraction of this from this channel, the other channel, and this. So each of these will have a certain overhead of communication. So if you're familiar with information theory, it will be like right. So you just, so this is like the overhead. So you'll have some overhead of actually sending few bits, and then it will like blow up like a log. Right, so you basically want to minimize this. Right, so it looks like a very simple problem, but like the form itself is like very ugly, and like this term is kind of like very annoying. You have a log term, and this, like we have seen a little bit of using logs, especially in the barrier method, so we'll come to that later. But so this itself is like very, looks very hard. So let's like review how you actually calculate the compute the dual for this, and then look at how the dual will look at for this problem. So I'll just write out the KKT conditions, and so once the first thing I can just, so these are my dual variables for this, right? So these are the dual variables for each xi, I'll have a ui, and for this constraint you have a v. Right, so I'm just taking the differential of this, right? And sorry. Right, so this is just the stationary condition, and like this will be a complementary condition, right? So for this constraint, right? So and you also have unit feasibility. Just writing those constraints. Feasibility, there is, of course, you want right. So I just wrote down the conditions, the KKT conditions for the problem. So I'll just rewrite those things, just like eliminating the variables ui. So I know ui is basically plus v, and I know that this is greater than or equal to 0, right? And I also write the same condition for complementarity. Right. So you get like you basically eliminated all the dual variables u, and you get this system equations, right? So you still have to calculate the feasibility of this. You need to find a solution for this, right? And you're done. You're done. So like this is like one of the key equality. You can see that either. So one of them should be 0. So if you know that is this minus ui? Yeah.
Oh, it looks like a plus.
Okay. Right. So okay. So if this condition holds, essentially you are saying that this is greater than this value. So ui is greater than 0. Basically, then this has to be 0. Right. So in that case, basically xi should be 0. It's basically then right. Otherwise, it will just be equal to 0. So it will be the other way around.
It's 1 by v minus alpha.
Right. And this should be the other way around, right? Right. Yeah. So basically your x, so you got like some form of x, right? So you have this system, and then you know that you need to satisfy this equality as well. So essentially you have, you look at this, it's just max of 0 and right. So if you just, so this is like you have reduced the whole problem, which is like in R, and to just a univariate problem. So now just you have to fit this value, and then you'll get the solution. So your goal essentially boils down to this single thing, that you want to find a V such that this sum will actually be equal to 1. So like this has a very nice interpretation. That's where you think of this water filling. So just like the way you do it is basically you sort all these alphas. So you have all these vectors of alpha. So now after sorting you have right. So essentially you want to find some 1 by V. Let's call this as V bar. You want to find some V bar which is basically has sum of all this. So you will have here minus alpha k. Right. So you just need to find this level where you can find the difference will be equal to 1. And the other way to interpret this is like, suppose you have so these are your alphas. So each of these levels basically tells you one alpha. This is alpha 1, alpha 2, alpha 3, alpha 4, so on. Right. So what you essentially do is you keep pouring water on this. So all of this increases. So first this keeps filling, or maybe this. At certain point, even it will be filling from here. Right. And finally, you want to fill in such a way that this sum, which is basically the level from here, will be equal to 1. Right. So essentially, we brought down the whole problem of, which seemed very unintuitive and ugly. It's basically this problem to a very intuitive problem and just univariate problem. So like this is one of good use of dual methods, where if you really want to gain intuition of the problem, you basically add new variables to your system, all these dual variables. And so in some cases even if you don't, over here we can actually, there's a natural reason to introduce dual variables, but in certain problems you can actually introduce constraints in order to introduce dual variables, in order to gain more intuition about the problem. For example, in graphical models you do a lot of message passing algorithms, which are other way to think about them is introducing dual constraints in a marginal polytope, or in a certain set of the graphical model inference problem. Right. So okay, so like that's the main point I want to convey in one of the uses of dual. Right. So any questions or? Okay, so now let's talk about penalty methods. So it's So now we have a good grasp of how to solve unconstrained problem, and the next step further would actually be to do constraint problem. And one thing which computer scientists do well or mathematicians do well is that you have a certain problem and then you want to reduce it to the problem which you have already solved, right? So that's essentially what you're trying to do with penalty methods. So you have, for example, just let's take a very simple problem. Right, so x, and you have this constraints, right? So or in general, this can be any function f of x here. So if you don't have any constraints, then it's pretty easy to solve what you have done, all your Newton methods, subgradient methods, or gradient methods. Right? So you can use any of those to solve the problem. So one natural thing to do would be to say, okay, let's say I'll just solve this problem. Right, so you have your whole constraint set. Ideally, you want to be just in this region. But what I'm saying is, okay, let me look at the whole region. I might be, away from the feasible region, but still, let's look at the whole domain rather than just looking at Ax equal to b. So I'm looking at the whole space now. So I can just solve this problem, and for example, if I keep increasing this gamma, so I'm saying that, okay, let's put more penalty if I'm outside this region. If I'm here, I'll say that, okay, this. So for example, if I just don't keep this, if I have, for example, just this, then one of the other points which are not in the feasible region can actually minimize this function. But what you're trying to do over here is that add another penalty term, which says that if I'm not in the feasible region, I'll pay for it. And so, like for example, I'll just take a guess where I just put gamma equal to 1, but you're still in this infeasible region, right? You're somewhere over here. Then I'll say that, okay, I'm still in the infeasible region. I want to decrease the function, increase the function value of this outside region. So let's put additional term. Let's put gamma equal to, multiply with 10. So gamma equal to 10. So I might still remain in the feasible region, or I might actually go to this region. Once I go to the region, I know that I'm more or less done, because there's some. So suppose you go from gamma k to gamma k plus 1, and now you suddenly jump from the infeasible region to feasible region. I know that somewhere in between this value, actually you will shift from here to this point. So it's a continuous function, so you'll be shifting from here to this point. So you will try different other values, maybe something which is like average of this. So it's essentially a binary search. You can do something like that and then try to figure out something which is in the feasible region. Right, so this is essentially the whole point of using penalty methods. And okay, so we already seen one kind of penalty in our from the first lecture, right? So we said that, so if we have some constraint set, then so we had the indicator variable which we used right from the first class. So this is essentially says this puts like infinite penalty if you're outside the region, and if you're in the region, then you're good. But the problem is still harder, because you're essentially adding something which is not differentiable, it's not even continuous. So so this is the problem. The problem is like as hard it was earlier, In some cases, you can use subgradient methods, or you can use projected gradient methods to solve this problem. But so essentially, what you're trying to do is relax this term over here. So you can add various kind of penalties for here. So your penalty function should be such that it will not penalize anything over here, which is in the feasible region, but it will penalize everything over the other side, which is the infeasible region. And you keep increasing the penalty in such that your end goal will be over here, right? So this is essentially so such kind of penalty is essentially like the theme across many algorithms, not just the penalty methods. For example, in Lagrangian multipliers, we are doing very similar things, right? So you are saying that you minimize let's make this more concrete. We'll say that right. So you're adding and you want ui to be greater equal to 0. So basically adding this penalty term. So it's not so you can over here we basically fix something over here and then try to solve over here, but we'll do slightly different things where we maximize over these dual variables. But essentially the theme is like very similar, where you have a penalty term over there and then try to solve this problem. And then this runs across like many other, and then suppose, so this is Lagrangian, so you can, there's something called augmented Lagrangian. So which says that you want to minimize over u. So here you have two terms, this Lagrangian term and the penalization term. So you are kind of like combining both of these, right? So and then you try to solve this problem. The advantage over here is that, so in many of the cases so one of the big problems with penalty methods is how to actually, so suppose you might actually have to make this very large. So you want this to be very large, so you put 100, it doesn't work out, so you put 1000, so you keep increasing your penalty. And as you keep increasing your penalty, your problem is going to be ill-conditioned. You want to solve this problem at the end. So if you want, for example, if I use Newton's method, so the problem will become like more and more ill-conditioned as you make the gamma larger and larger. So in augmented Lagrangian, you can show that you don't have to take it to, for example, potentially infinity. Your sequence need not be infinity, but you can stop at a certain point, but still you can get convergence. And essentially your Lagrangian multipliers will take a certain part of the role of the penalty function over there. Right, so, and, right. So there's also some connection with how this value, how large this value need to be. For example, you'll show in the homework that this gamma will be should be greater than your Lagrangian multipliers if you solve your Lagrangian multiplier problem. This problem, so if you get the optimal solution, ui bar, you need C to be greater than ui for all I. So if you choose this, then you're solving an equivalent problem as your original problem. Right, so any questions on this or?
said about if you find gamma k plus 1, if gamma k is outside the set and gamma k plus 1 is somewhere inside the set, then you can search for something in between. I think at the point that it's inside the set, you're immediately done and you have the optimum.
But you can choose your gamma as like, so suppose I chose it as like 10. After that I chose like 20,000. It depends upon the sequence, right?
No, but I think as soon as you find a point inside the feasible region,
But that need not be.
I claim that that's the optimum solution to the original problem. That's my claim. So, and the reason is that the value that your function takes, so at gamma k plus 1, the value that your function takes will be C transpose x, I mean C transpose x star, whatever x star you found. So I call that x k plus 1 star. Because you put gamma k plus 1, let's call it x k plus 1 star. Your value is C transpose x k plus 1 star. Now, when you put your gamma k plus 2, which is somewhere in between, the value that you're going to
Right, your penalty function is basically 0 over your region, so it should find your, right.
It will find the
Right.
so
Yeah, true.
K2 star,
Right. True. So I take back that statement. So as soon as you find it, then you're done. Although you don't want your gamma to be very large, again your subproblems will be confusion. Yeah. Right. True. So finally, we'll look at interior point methods. Okay, so this has like a very similar theme as what we are doing. So in penalty methods, if you have your minimum somewhere over here, what your sequence of optimal values will be something like here, and then you'll basically reach here, right? So you see, you're going from your infeasible region and then to your feasible region. And interior point method is kind of like a complement of that, where you really don't want to go outside your region, but you want to stay here. And for example, I'll start somewhere from here. Suppose I get a feasible point, and then somehow I'll follow this sequence and get those optimal solutions. So it's like a complement to a penalty method, and it has again has a very similar flavor to adding a penalty, but you'll add a penalty in such a way that you'll never go beyond this region. So it's kind of like you have a fence or a barrier in your feasible region, and you'll never go outside this region, right? So you'll add a penalty term in such a way that you'll never go outside this region. Right, so assume that you have again very simple case, and so what I'm going to solve, again I'll reduce it to a unconstrained problem again, and for example I can add this function. Let's make this greater than 0. Right, so I added this term over here, and if you look at this, then as long as you're going as close to 0 this will blow up. Right? It will go to minus infinity. This will go to plus infinity. So this is going to be very large. So essentially, you can never go beyond this point. You can't even go very close. So you can go to this region, and then there'll be like a strong force, a repelling force over here, and then it's kind of like you'll come back. So you never want to go very close to your barrier. And if your optimal solution is like close to the barrier, then you'll expect to take more number of iterations. Then it's not if it's not close to your barrier over here. Right, so okay, so this problem itself looks very horrible. So you introduce like a log term over here, and you have a good set of constraints over here, and then so this itself is like doesn't look very well. But once you try solve it, like Barnabas has actually worked out the whole thing, so it works out well, and you'll get so each subproblem can actually be solved using Newton's method or any of those. So it should actually be one. So you will take this to be, you will increase this value of t. So you will decrease the barrier repulsion at each of these points, and then try to find the optimal solution. So if your optimal solution is this, initially there'll be a huge barrier to come to this point, but as you decrease your repulsion force over here by increasing this value of t, you'll slowly come very close to the optimal solution. So you'll never reach your optimal solution, but you'll get arbitrarily close to your optimal solution. Right. So I'll talk about a slightly different way of actually doing interior point method. So okay, so the main motivation is, suppose you have a feasible region. Somehow I want to find a good a set where you can easily optimize, number one, and which is easy to find. Right. So these are the good motivations for finding a good feasible region. So this itself is not good. For example, I can try to build an ellipsoid in this feasible region. So let's not worry about the details of how to find this, but suppose I find this. Now I have an ellipsoid. Say suppose then so I find this ellipsoid, and now I'll optimize my function over this ellipsoid. I'll just optimize subject just in this feasible region, right? So this is going to be my optimization problem. So there are two problems. One is how to find this ellipsoid, a good ellipsoid. So I can always find a very small ellipsoid over here, which is like very useless in many of the cases. But I want to find a good ellipsoid, which is a good summary of the feasible region, and also like easy to optimize. Right. So Daikin's ellipsoid is like one good way of doing this. So I'll just describe what the ellipsoid is actually. So if I find an interior point, suppose I know this point. Right, so my phi is basically my barrier function over here. It is basically minus of log. right? So h of this is basically Hessian of this barrier function at point x0. That will give me my this matrix. So this is positive, definite, and things work out well. So this is basically essentially your ellipsoid. So all x so you can vary these terms as well. So that will we'll not talk about that, but we can also vary this. You're varying your kind of like radius of your ellipsoid. Right, so this is my ellipsoid. Now I'll just optimize this. So over here it will just be x0. Optimize this over this region. So the good thing about this ellipsoid is that if you take this,
What is phi?
so this is a barrier function. Any barrier function you can use for your feasible. So over here you just use log, minus log of it, but you can potentially use this, for example, 1 by your function, your constraint. That's another barrier function. So it basically depends upon how well you can optimize these things, right? So if I call my feasible region as f, what we can show is this ellipsoid will actually be inside your feasible set. So that's good. So you'll always be inside your, this constraint will make sure that you will always be inside the feasible region, and then you're minimizing this function, right? So, and as long as you're not at the minimum, you can always find a certain region, a certain scaling factor, such that you'll stay inside the region, and then you'll also like optimize over a region. So you'll always move to a better position. You'll not be stuck at a point. So you'll always make progress in your optimization. Right. So how good is this ellipsoid itself is like a bit of a problem actually. So if I take this ellipsoid at I'll define what is x a. So suppose I have a linear constraint. So suppose I have x equal to b as my constraints, and this is m cross, and so I have a polyhedral. Now I know that what we can show is that if xa is the minimum of x, this barrier function, then this will cover pretty good part of your feasible region. So you can show that your ellipsoid will actually be a good summary of your whole feasible region. Right, so you can always start with that point and then keep continuing in this fashion. So this is also called, so this whole procedure is also called affine scaling. So I didn't mention few details, like for example, I can always, so this is actually greater than equal to, like you can add more constraints to this. So to this example some C. So I can make, I can also like include equality constraints and still solve this problem. but now the problem will become like more complex, and you have to actually have some kind of mechanism to project onto null space of this matrix, which is not very hard. Right, so any questions? So one final remark about this is that how do you find this feasible point initially? So for all these algorithms, you need to start with some feasible point, feasible interior point. So how do you actually find the feasible interior point? That's like a question. So suppose I have again this same question, right? So I have I want to start with something where I have but what I can essentially do is try to solve this problem. So this is like more like a feasibility problem. Now I'll solve this problem. So I'll try to minimize all these functions as much as possible. So I'll get I can use any of my, for example, I can just use. So now I have, it's easy to find a feasible solution for this, right? So if you can easily find the initial point for this, I can use any of the interior point methods for solving this problem itself. So I'll get some solution to this, right? So I can now look at what's the value of p. So if p is going to be greater than 0, then there's no absolutely no hope of actually finding a feasible point. Then basically you can't find this. So you'll basically give up on it. And if p is less than 0, you found some interior point, right? So and then I can get a feasible point from this itself, the solution of this. So p equal to 0 is a bit tricky, where so it basically depends upon whether this actually attains this value. So suppose this is actually pretty good, but if you have some more constraints, for example, if I have additional constraint that ax equal to b, so I can have my optimum value to be 0, but still it may not be a feasible point. Right, so you have to see whether there's something which actually attains this value. So you can just basically solve this problem, try to see what's the sign of this value p, and then determine the initial point for your rest of your algorithm. Right, so yeah, any questions or? So I'm more or less done. If you have any questions, then. Cool, then, yep, you're done.